Let's now take a look at the idea of univariate hypothesis testing. As usual, let's start off with the learning objectives. First thing we want to do is understand the logic behind a hypothesis test for a population parameter. It's really important that you understand that all this hypothesis testing that we're going to be doing, it's all about population parameters. It's not about the statistic, it's about the parameters. Keep that in mind. We use the statistics to address the parameter values, but it's all about the parameters. We want to construct and interpret a test of hypothesis for a population parameter, identify appropriate parameters to test based on the data, and comprehend the types of statistical errors that can be made in the decision-making process for a hypothesis test. Okay, the logic behind hypothesis testing. Univariate hypothesis testing is a technique that allows us to compare the value of an observed sample statistic with a believed parameter value. So we're going to have a value that we believe is the true value, what we think is the parameter value, and then we're going to compare it with a test statistic to see if logically that's reasonable. Is it reasonable that this parameter value may be accurate, or is it more likely that it's wrong and the true average, true proportion, true median, whatever, is really something different? Now, suppose you believe a new treatment for a particular form of cancer will increase survival rate. The current average is 2.25 years. So whatever technique they're using right now, the typical survival time is 2.25 years. Now, average from your test of 13 persons resulted in an average of, say, 3.1 years. Now, you don't have to have a degree to figure out that 3.1 is bigger than 2.5. But remember, there's randomness involved here. If we took another group of 13, certainly we're going to end up with a different average survival time. It could be less than 2.5. It could be more than the 3.31. There's a lot of variability. Who knows what exactly it could be? So, what we need is a process to take a look at this 3.31, which we're thinking of as our sample average, or perhaps sample median, and compare it to what's happening now, the 2.5 or 2.25. Does the fact that it's bigger, the 3.1 is bigger, is it big enough? Is it far enough away from that 2.25 years to suggest this average really should be bigger? Now, the logic behind it, a hypothesis test would give us a way to make that determination, whether the 3.31 suggests the average is actually bigger or not. And we do this based on probabilities. All the decisions that we will make will be based on probabilities that we will be calculating. The technique will help us decide if the difference between a sample statistic, that 3.31, and the believed parameter value, 2.25, is simply by chance. Is it random error? Any other group could end up with something different. Or is it more likely real? Is it more likely that this new treatment really does result in higher average survival times? Or is this 3.31 just a fluke, just by chance? That's the basic idea what we're trying to get at here. Now, the hypothesis statement is a statement of something that is believed to be true. Okay? So, a hypothesis test is a process by which a decision is made between two opposing hypotheses. So what we're going to do is we're going to set up two hypotheses. They're going to oppose each other. And then based on those probabilities, we'll make a decision as to which way we think we should go, which is more reasonable. Now, the two opposing hypotheses are known as the null and the alternative. The null and the alternative hypotheses. These are two statements that we will make and use data analysis to actually test them. Now, the null hypothesis we denote by H0. H is a subscript of 0. It's a statement of what I think of as being the status quo. The status quo meaning simply it's what's expected to happen, what's been happening. It's the typical, that's what I mean by the status quo. And then the alternative hypothesis, well, we get that in a second. In the cancer example, we're going to assume right away that the new treatment is actually no better than the old. So that will be our null hypothesis. We're going to start off with the idea of there's no difference between the new treatment and the old treatment. They're the same. So the new treatment is the same as the status quo. It just fits in with the status quo. So the null hypothesis will read H naught, and I'm talking about the mean, so I will say mu equals 2.25. That's the believed value. This 2.25 is the believed value of the true average survival time based on what's been going on. Now the alternative hypothesis, which we denote by H with a subscript of A, is what I think of as the research hypothesis. This is what you're trying to show is more likely. You're trying to show that this is more likely than the null hypothesis. This is a hypothesis research is typically trying to suggest is, as I said, more likely than the null hypothesis. For the cancer example, we would write the statement as H sub A, the alternative hypothesis, mu is greater than 2.25. Now, notice that nowhere in here does the test statistic show up. The sample statistic does not show up anywhere in the null or the alternative hypothesis. Not the values of the sample statistic, nor the symbols for the sample statistics. None of it does. This is all about the parameter value. So we're making statements about the parameter. And we will use the sample statistic to actually make a determination, but the statement itself is about the parameter. Hypothesis testing is always about population parameters. They are not about the sample statistics. Again, we use the sample statistics to make a decision, to calculate probabilities about the population. But the emphasis, the concern is with the population. Now, a hypothesis test is actually what's known as an indirect proof. Researchers gather data in hopes that the data will contain sufficient evidence to suggest the null hypothesis is unlikely, or you may think of it as saying it's false. We're trying to suggest that the null hypothesis is false. So if the null hypothesis is shown to be unlikely or false, then the alternative hypothesis, the only one that's left, is then more likely. So if we reject the null hypothesis, we say that we don't think this is very likely, then the other hypothesis, because they're opposing, you only have two situations here, either the null or the alternative. If you get rid of the null, then all that's left is the alternative. So you say, this is what the data is pointing to. The data is suggesting that this alternative hypothesis is more likely than the null hypothesis. Now, keep in mind that this is not proof of anything. We really cannot prove anything with a hypothesis test. Rather, what we hope to do, we hope to suggest the likelihood based on probabilities. It's not really proof. You've got to be careful when you say the word proof. In a strict mathematical sense, it is not a proof. It's just evidence that piles up against the null hypothesis in favor of the alternative, or a lack of evidence. You could go either direction.